Welcome to a fantastic voyage throughout the entire universe. We live in a golden age of astronomy. Discoveries are being made with powerful instruments such as the Hubble Space Telescope all the time, and they are frequently reported in the news. It's just incredible. You go out, read the newspapers, and there are all these cool things. Black holes, planets around other stars. You name it, astronomers seem to be finding it. This visually rich course is a completely updated version of my previous sets of astronomy lectures taped in 1998 and 2003. I thank the teaching company for inviting me back for this second edition, and my family for their support during the extensive preparations. I have 5 major goals in this course. The first is to share the excitement and magnificence of the universe with you. How does the universe work? What are the coolest new results? I'll cover so many provocative, mind-boggling topics you won't know what hit you. The second goal is to give you a basic understanding of astronomy and kindle your Socratic flame. This is, after all, a survey course, and so it can do that. It can kindle your flame because Socrates said, education is the kindling of a flame, not the filling of a vessel. You need to know at least a little bit sometimes in order to even know what questions to ask. The third goal is to show you that astronomy is a quest for our origins, our place in the cosmos. How did we get here? Where are we going? What will become of us far in the future? The fourth goal is to give you some idea of how science is done and to convey the thrill of scientific discovery. Why are scientists so addicted to this process of figuring out how nature works? Well, I hope to show you some of that thrill. And then, finally, I hope to heighten your sense of awe and wonder about the cosmos, to increase your curiosity about nature, so that you'll go out, look up at the skies, wonder what's out there, and want to go and explore what it is that scientists have figured out about the workings of the cosmos. Now, astronomy is a physical science, so some physics and math will be involved, but this will be minimal, and I'll explain it along the way. You can understand the main ideas without concentrating on the math at all, if you wish, but I'll have some of the math there for those who want to see some more of the details of what I'm talking about. But I'm not going to fill the blackboard full of equations that are incomprehensible to anyone except for the experts. You know, you're not going to see this kind of thing in this course. I'll give you a little bit of the math so you can explore more deeply if you wish. But again, you don't need to pay attention to the math at all if you don't want to. A broad outline of the course is as follows. I will start with a major part on observing the heavens, the first 24 lectures or so. And this will consist of 3 units, celestial sights for everyone, the early history of astronomy, and then basic concepts and tools that astronomers use. I'll then move on to the second major part of the course, and this will be the longest part by far. And it'll consist of 5 units, one on the solar system, the second on other planetary systems that are being found, the third unit will be on the stars and their lives, the fourth will be on stellar explosions and black holes, some of the most exciting and exotic topics of the cosmos, and finally the Milky Way galaxy, our home, and other galaxies. The third major part of the course will focus on cosmology, the universe as a whole, and it will consist of 3 units. The first will be cosmic expansion and distant galaxies. We will use the fact that the universe is expanding to derive the distances of distant galaxies, whose distances can't be determined in any other way, and we will then use those distant galaxies in the second unit of this third part of the course to explore the structure and evolution of the universe as a whole. And finally, in the third unit of the third major part, I'll discuss the birth of the cosmos and other frontiers. Now, cosmos means the universe, all that there is, but specifically the universe when regarded as an orderly, harmonious whole. So I've written a book with my co-author, Jay Pasakoff, called The Cosmos, Astronomy in the New Millennium. And it is the primary reference book for this course. If you want to explore in more detail the things that I'm talking about, you can consult this book and read about these topics at your leisure. It goes into more detail on some of the topics, less on others because of constraints on the length of the book and my personal preferences, so I'll explore some of the things more here. And the order is somewhat different in a few places, but most of the topics are covered, and you can of course consult other books as well, but that's the one that I recommend given the structure of this course being similar to that of the structure of the text. It's published by Thomson Brooks Cole. Now, it seems natural in a grand tour of the cosmos, the subject of this lecture, to begin with celestial sights that everyone can see and appreciate, like rainbows. You look out into the sky and you see during the day rainbows, beautiful colors. How are they produced? It turns out it's not so hard to understand how light is bent by droplets of water into a rainbow or spectrum of colors. The spectrum of colors is also seen in the soft orange or even deep red glow of sunsets. How are those colors produced? Well, we'll understand how, and we'll see how an understanding of this relates to some celestial phenomena. There are clouds of gas called nebulae which glow for similar reasons, and they have many different colors. We'll look at some of the brightest, most easily recognized constellations and patterns or asterisms in the sky, like the Big Dipper. And we will explore what produces shooting stars. Now, they're not stars at all. They're actually little specks of dust or grains of sand or small pebbles zipping through Earth's atmosphere, heating up due to friction and causing this streak of light. So they are not stars becoming unglued from the celestial sphere. Then we'll explore auroras, the northern and southern lights, the glow produced by charged particles from the sun interacting with Earth's atmosphere, kicking electrons in atoms and molecules up to higher energy levels, from which they then cascade down, producing these northern and southern lights. A beautiful phenomenon. We'll explore the clockwork of the universe, the fact that when you look out into the sky, you see, for example, over the course of the night, the rotation of the stars around the north or south celestial pole. And then the clockwork of the seasons as well, how summer and winter change, and the sun's height above the horizon varies with time of year, and how at some places on Earth, like the South Pole and the North Pole, you can see the sun above the horizon for 6 continuous months, and then darkness for 6 continuous months. What about phases of the moon? How are they produced? You look at the crescent moon in the sky. Is it due to clouds or something like that in the way? No, it's a geometrical effect. It's dependent on the relative positions of the sun, the earth, and the moon. And we will explore how it is that the phases of the moon are produced and can be understood and followed on a day-to-day basis. Now, sometimes the moon goes into the shadow of the earth, producing a lunar eclipse, an eerie glow reflected from the moon because some of the sunlight is not blocked by Earth, but rather goes through Earth's atmosphere and is bent toward the moon. And the orange glow is for a reason similar to that of the orange glow at sunset. Occasionally the moon passes between us and the sun and partially eclipses the sun. It's like a bite has been taken out of the sun. And when you get a total solar eclipse, when the moon completely blocks the sun, oh, what a glorious phenomenon. If you've never seen a total solar eclipse, you have got to see one. My first one in 1979 left an indelible impression on me, and I have since then seen 7 more, and I plan to continue chasing eclipses for the rest of my life. I am addicted to eclipses. We will then consider the early history of astronomy, starting with Aristotle, whose view was that the Earth is the center of the universe and everything rotates around it. Of course, Ptolemy came up with a more complex system expressing in some detail this geocentric view, where the Earth is the center and everything else basically goes around it. But in Ptolemy's system, there were epicycles and various complexities that allowed one to calculate where the planets should be any given month or day or year. It was very useful for astronomers. But Copernicus led to a revolution where he felt that the sun, not the Earth, is the center of our now called solar system. And he did not know that this is the case. He just postulated it. But Galileo made observations which proved that the sun, not the earth, is the center of our solar system. Galileo was one of the giants. He also noticed that there are moons going around Jupiter, suggesting that other bodies, not just Earth, could have things orbiting them. And here, two of the moons cast shadows, and there the shadows merge, and you would get a double eclipse of the sun if you were on Jupiter at this moment. It's really great. Galileo's observations also showed that as Jupiter moves through the sky, the moons move along with it. They're not left behind. And so perhaps in a similar way, when we jump above the Earth's surface, the Earth is moving yet not leaving us behind because we're moving with it. This was a key intellectual advance in the history of astronomy. Now, Isaac Newton took Galileo's observations and formulated his laws of motion and his law of universal gravitation. He unified seemingly disparate phenomena like the falling of an apple and the orbit of the moon around the Earth. And we will see throughout the course that there's this grand unification of seemingly disparate phenomena, all understood using the same, much smaller set of simple laws. What are the basic concepts and tools used by astronomers today? Well, we need to gather light, and we do that with telescopes, but an important aspect of light is that it doesn't travel at an infinite speed. So as we look at objects of progressively greater distance, we see them at progressively greater times in the past. Light takes time to travel from there to here. It goes at about 186,000 miles per second, or 300,000 kilometers per second. If you multiply things out, that's 6 trillion, or 6 million miles per year. So when you look at a star that's several light years away, you're seeing it as it was in the past. And if you collect light from a galaxy like this one, the Andromeda galaxy, you're seeing it as it was about 2.5 million years ago. You're looking back into the past, and you get a movie of the history of the universe as you look at progressively greater distances, like all these faint fuzzy galaxies, billions or even up to 10 billion light years away. We can collect the light and spread it out into a rainbow or a spectrum, learning about the chemical composition of the stars producing that light, and learning all sorts of other interesting aspects of their structure. The light, as I said, is collected with telescopes because it's feeble. From distant stars and galaxies, you can hardly see the light unless you use a large telescope to collect that light. And there are ground-based telescopes as well as space-based telescopes, most notably the famous Hubble Space Telescope, which has revolutionized our view of the cosmos. Moving on to the solar system, we will examine briefly the solar system's contents, starting with our sun, which is active. It's always changing with time. You can see here a movie of our sun over the course of, at first, several hours and then several days. And you can see that its surface is teeming with activity. And occasionally there are these jets of gas that come out, prominences. You can see them spouting off here all over the surface of the sun. And there's one off to the side on the edge of the sun. And oh, there's a tongue of flames almost coming out of the sun. The planets orbiting the sun are, of course, the Earth and Venus. Venus initially seems like a hospitable planet until you study it in greater detail, and you find that it's sort of like hell. It's got a really, really high temperature. We couldn't survive there. Mars is a little bit nicer. You can see Mars in two views here. One, a normal view, another one during a global dust storm, which prevents us from seeing surface details. And then there are the giant planets, Jupiter and Saturn. Oh, a lovely planet, just lovely. And there are many moons like this one, Io, a moon of Jupiter on which there are over 100 active volcanoes at any given time. It's the most volcanically active body in our solar system. And then we will address the question of whether Pluto is really a planet or just one of a vast collection of rocky, icy bodies beyond Neptune, some of which sometimes come close to the sun, get evaporated by the sun's heat, and then reflect the sun's light, forming a luminous comet. Other debris in our solar system includes the asteroids, primarily between the orbits of Mars and Jupiter. And sometimes they wander away from those locations and they can hit the Earth, causing gigantic explosions and leaving big craters such as this one in Arizona. One such collision of a comet or an asteroid is thought to have destroyed the dinosaurs and 2/3 of living species 65 million years ago. We know that such collisions can occur. In 1994, we saw a comet that had been disrupted into 20-some-odd pieces go crashing into Jupiter. One by one, these pieces crashed into Jupiter. Wham! 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 Releasing tens to hundreds of thousands of times more energy than the most powerful nuclear weapons known on Earth. We'll move on to other planetary systems. How did they form? Well, they form from giant clouds of gas and dust, gravitationally contracting to form central glowing objects surrounded by disks of debris, gas and dust that can in principle coalesce to form planets. And we see these disks of debris around some young stars. And there's even a lot of evidence now for planets, real live planets orbiting other stars. About 200 planets outside our solar system are now known. It's incredible, and they were found just in the last decade. This, of course, rekindles our interest in the question, is anybody out there? One of the greatest mysteries of all time. Well, you might say there's lots of evidence for other creatures being out there. Look, here's a publication that says that an alien endorsed the Texas governor, and ecstatic aides said that he's a shoo-in as a result of this. Well, of course, don't believe everything you read in newspapers and tabloids especially. It's a legitimate question. Did life, complex DNA or something like it, form elsewhere? And did it evolve up to a state of intelligence comparable to or even exceeding ours, where it can contemplate the vastness of the universe and its contents? We don't know, but we're trying to find out. And we're trying to find signals from possible extraterrestrials intentionally or unintentionally communicating, sending electromagnetic waves through space. You can find them. You can detect them in principle using large radio telescopes. And we'll even explore the possibility that one could traverse the vastness of space in a spacecraft and visit other stars, other planets. It turns out to be very hard to do. The stars and their lives will be our next topic. We will consider their distance, size, power. It turns out stars come in a variety of sizes, like Betelgeuse, the upper left shoulder of Orion. The constellation Orion is a giant star which would go nearly out to the orbit of Jupiter if Jupiter were orbiting that star. It's a supergiant. Stars orbiting one another allow us to determine their masses. By studying the mechanics of their motions, you can figure out their masses. And looking at clusters of stars, you can figure out ages of stars. Here's a cluster that happens to be fairly young. It's an open cluster. Here's a much more concentrated globular cluster, which is 12 to 13 billion years old, one of the oldest objects known in the universe. And we will explore how it is that stars produce the energy that we see. They do it through nuclear reactions deep in their core, the fusion of hydrogen into helium, and later in their lives, the fusion of helium to other heavier elements. Now, some stars aren't quite massive enough to fuse hydrogen. We call them brown dwarfs. And here's a little one in orbit around a normal star. And this brown dwarf is barely glowing. It's very difficult to detect. But our sun, of course, is bright. It's got a lot of nuclear reactions going on inside. Will it last forever? No, it won't. Later in its life, it'll blow out its outer atmosphere of gas in gentle eruptions, or cosmic burps, I like to call them, forming a glowing nebula with a dying central star in the middle. That'll be a beautiful sight. And in the end, the sun will turn into a highly compressed remnant, a white dwarf, comparable to the Earth in size, but having a density, a mass per unit volume so high that a teaspoonful of material would weigh several tons. We will then explore explosions of stars and black holes. Some stars explode at the end of their lives, releasing material that gets ejected into the cosmos. And this material is chemically enriched in heavy elements because the explosion produced those elements and also liberated the heavy elements that had been previously produced by nuclear reactions in the normal course of the evolution of the star. The remnants of such explosions, like the Crab Nebula, go flying out, and from that enriched set of gases, new stars and planets and ultimately life can form. Well, at the center of an explosion, you sometimes have a compact remnant called a neutron star, a star having roughly 1.5 times the mass of our sun, but compressed into a volume whose radius is only about the size of a city, maybe 6-mile radius or something like that. Incredibly dense material, like a gigantic atomic nucleus. Such an object bends or warps space and time around it. And if the object is sufficiently compressed, the warping of space and time is so extreme that nothing, not even light, can get out, and that then is called a black hole. And here's my prize-winning photograph of a black hole. Black holes can be detected by their gravitational influence on companion stars, which are sometimes bound to them. You can actually see material that the black hole is stealing from the other star, and that betrays the presence of the black hole. And theoretically, at least, some black holes might provide passages or wormholes to other universes. Can you really go through one of these wormholes? It turns out you can't, probably, but the mathematics suggests that in an idealized case, you might be able to. Black holes form, in some cases, we think, by the collapse of very massive stars, which produce momentarily a brilliant burst of radiation, often at high energies, gamma rays. And some of these so-called gamma ray bursts might also be produced by the merging of two neutron stars or of a neutron star and a black hole. Bam, there it goes, increasing the mass of the black hole and forming two jets of material that are oppositely directed. This coalescence of neutron stars or neutron stars and black holes should lead to gravitational waves, ripples in the very fabric of space-time that go out from the coalescing neutron star, betraying its presence if we someday detect or build detectors that are sensitive enough to actually find this radiation predicted by Einstein's general theory of relativity. We'll then move on to galaxies, first considering our own galaxy and the sun's position in it. Let's take a journey through our Milky Way galaxy, exploring its contents and its structure. We head toward the familiar constellation of Orion. You can see the stars of the belt, and below them is the sword of Orion. Inside that sword is a giant cloud of gas and dust, forming stars right now as we speak. It's a gigantic stellar nursery about 1,500 light years away. We move past other such nurseries, the Horsehead Nebula, where again stars are being formed as we speak. And there are nebulae throughout our galaxy, sites of active star formation. This one here, the Rosette Nebula, formed some very massive luminous stars which subsequently blew a bubble around them, a hole in the nebula. Moving on, out farther from the sun, we go past the Crab Nebula, the remnant of a colossal explosion that was seen by Asian astronomers about 1,000 years ago. There are chemically enriched gases in those clouds, gases which will later form new stars, planets, and perhaps life itself. Moving out of the plane of our Milky Way galaxy, we begin to see its true grandeur. We can't get such a view from within. But from above, we see the beautiful spiral structure and the companion galaxies, the large and small Magellanic Clouds. We live in a cluster called the local group, consisting of a few dozen galaxies. The major companions in our local group are the Andromeda Galaxy, seen at left, and another one, M33, through which our journey takes us. There's a giant nebula, a stellar nursery in M33, and we whisked right through it. Now we will go and explore other galaxies, ones that are outside our local group. You can see very distant ones back there, but here we go right past M81 and M82, just 11 million light years away. And here's another one, M101, a beautiful spiral galaxy, and then the Whirlpool galaxy, M51. Looking at this vastness of space, we see all these fuzzy little blobs, other galaxies like our Milky Way, like the Andromeda galaxy. There are thousands of them. We first go through a loose group called the Ursa Major cluster. And then we turn and head toward a massive, giant cluster of galaxies known as the Virgo cluster. It's about 60 million light years away, and it contains over 1,000 galaxies. The central galaxy, M87, is enormous and has cannibalized small galaxies in its vicinity, and we think it even has a gigantic black hole at its center. Turning finally to cosmology, the universe as a whole, we will first consider cosmic expansion. You look at all the galaxies and they appear to be moving away from one another. We think the whole grid of space, the whole coordinate system is growing, and the galaxies themselves are remaining about the same size, but their distances from one another are growing. We can use this relationship, speed of a galaxy versus its distance, to determine the distance of a galaxy by measuring its speed of recession away from us. And knowing the distances of galaxies, we can then figure out how far back in time we're looking. If we examine extremely distant galaxies, billions of light years away, we see that they look different from our Milky Way and other nearby galaxies. Galaxies evolve with time, and by looking at progressively more distant ones, you can monitor that evolution. Looking in the hearts of some galaxies, we will find evidence for supermassive black holes, millions or even billions of times as massive as our sun, devouring material in their immediate vicinity. And the most extreme example of this are the quasars, extremely distant, luminous denizens of the distant past, where a black hole is devouring material at a prodigious rate. We will then consider the structure and evolution of the universe as a whole. What is its overall shape? What is its size? When did the universe begin, and how will the universe end? Is our universe like an infinite flat sheet of paper, but in 3 dimensions? Or does it wrap around itself, like the surface of a sphere? Or does it curve in a negative way, like the surface of a horse's saddle? There are ways we can tell by testing various geometric properties of space. And we can also look at when the universe might have started by extrapolating the observed expansion of the universe back in time to the Big Bang, the beginning. When did the universe begin? Extrapolating forward in time, how will it end? Will it keep on expanding forever? Or will it recollapse when gravity takes over and causes all these galaxies to collapse in on each other to a big crunch, the inverse of the Big Bang? Well, we now think that that's not going to happen. We think that based on today's information, the universe will either expand forever or for a very long time. And that's because observations of distant exploding stars, supernovae, actually tell us that the universe right now is expanding more quickly than it was 4 or 5 billion years ago. The expansion of the universe is not slowing down with time, it's speeding up, as though the universe is filled with some sort of a cosmic anti-gravity. Imagine Einstein's reaction if he were alive right now to hear this conclusion. The reaction might have been something like this. Observations of the afterglow of the Big Bang, the faint hiss at radio wavelengths that fills the universe, confirms these ideas that indeed the universe seems to be filled with some sort of a dark energy causing a cosmic repulsion. That dark energy dominates the total energy and mass of our universe. 3/4 of it is some sort of weird, repulsive stuff. Most of the remaining quarter is dark matter of an unknown type. We don't know what it is. What's the dark energy? Who knows? But it might be quantum fluctuations in space itself, Or it might be related to theories that postulate the existence of other dimensions, spatial dimensions that are wrapped around on such small scales that you can't see them, kind of like the granularity of a sheet of sandpaper. Finally, we will consider the birth and origin of the cosmos and other frontiers. We will see how early in the history of the universe, the lightest elements and their isotopes were cooked up in the fiery bath of the Big Bang, primordial nucleosynthesis. And we will see how unified theories of the forces of nature may even explain how the universe began and how it grew to such a monstrously large size early in its history, like a balloon being inflated by a tremendous factor. Where did the universe come from before inflation? Well, we don't know, but it may have been a quantum fluctuation out of nothing, the ultimate free lunch. And indeed, there may even have been multiple cases of universes in a grander structure, the multiverse. I'll end in the last lecture on a philosophical note with some reflections on life in the cosmos and of our place in the grand scheme of things. It's amazing to me that we humans have the intellectual capacity to ask deep questions and to devise methods for learning how the universe works and how its contents evolve with time. Get ready for a fantastic voyage through the universe. We will explore just about all of the major topics in astronomy. I promise you a ride that you will never forget.